All right, everybody, I think I'm going to go ahead and get started. Thank you guys so much for being here. It's been a long time, my goodness. We had not only a spring break, we sort of had an extended spring break. My spring break got all messed up. I was supposed to go fly to the East Coast, and I had this trip, and I had booked everything in advance, and then the weather was horrendous. It was supposed to be horrendous the whole time. So I canceled the trip and instead had some people come out and visit me. But this was on the very last minute. So of course they couldn't just like fly out and fly back whenever they wanted. So they couldn't get out of here until this morning. I've actually been up since 4 o'clock this morning. They had a flight from LAX at 6 a.m. and I had to drop them at the airport. So, and I'm not a morning person. So if I seem like I'm not in a good mood, it's probably for that reason. Or if I seem tired, it's probably because I've been up for about 5 hours longer than I normally have at this time. But anyway, they took off just in time to avoid the heat wave, I think. But hopefully you guys had a good spring break as well and enjoyed a little extra time to get back into the flow of things. I'm going to make a few brief announcements before we get started again on things. The first one is that you probably all watched a video. I had 4 videos for you to watch. I checked this morning. It looks like just about everybody did it, which is to watch some video content that was what I would have done on Monday. And I've kind of got it summarized all over here. We're going to go through that in a moment. I'll refresh your memory on that. So thank you very much for doing that and taking those notes and submitting the video and everything. That's really a big help to keeping us on schedule. There is a homework assignment due tonight. It is a short assignment. It is just one section. I will be around for office hours this evening, starting at 5:30 to 6:30, and then I'll be back after 8 o'clock again. So if you have questions on the homework that's due tonight, feel free to swing by my office or Zoom, either way. I'll be back to my regular office hour schedule. The next homework after tonight's homework will be, I have posted it now. It's due on Monday, and it is going to cover a lot of what we're going to do today. So there is no homework for Friday this week. We have a Friday without an assignment, and you can just work on that next assignment over the weekend. So that's where we're at with respect to homework and stuff. We are basically into the final 1/3 of the semester. We have one more midterm before final exams. That midterm is actually on the Monday of the week before finals week. I do this on purpose because whether you realize it or not, when you're studying for the 3rd midterm, you're really studying for the final because the material, of course, is building on itself. And so everything that we're learning goes back and uses the stuff from before. We're going to see that a lot today, actually. Okay, so but even with the 3rd midterm, it's still about a month away. So we have some time to cover this last part of the course. We're going to finish chapter 6 today, and then we're going to get started on to chapter 7, actually, which is the last chapter on just straight linear algebra. So that's kind of where we're at. Anybody have any questions about that? I did grade your exams. It feels like an eternity ago. I graded them right away, like the first day after you took them, I had those done. The scores have been up in Canvas for a while. The solutions to the midterm were posted. So all of that is there. And I will pass back your exams to you at the end of class today. I don't have to do it right now or everybody's going to be distracted looking at those. But I will give you back your exams in a little while. Overall, they were reasonable. There was a big spread. There were some people who basically aced it. And then there were some people who I feel like really could use a little extra help to kind of get up to speed with things. But overall, it was a reasonable results, I think. Lastly, one other comment I want to make now is the university has sort of suspended worrying about masks. I see a lot of you have masks on, not all of you do. Masks are no longer required, and I can't enforce it, and I can't tell somebody they have to wear a mask or anything like that. I would prefer if people would still, so I'm gonna probably be the last one to take the mask off someday in the future. That's only because I have enjoyed not getting sick for the last 3 years. It's been actually quite nice. So I'm going to probably stick with it. It's up to you what you would rather do. I prefer if you wore a mask most of the time, but if you don't have one, or it slips your mind or something, or you just don't want to, I'm not going to, force you to wear one. It's not something you have to do, but I just wanted to give you that update about that. So I think that's the only changes as far as that goes. Any comments, any questions about where we're at? We're so good? Okay, fantastic. Well, yeah, it has been a while. So I think I should spend a little bit longer time than normal to kind of recap where we were as of before spring break. We were talking, if you remember, we were talking about linear transformations. These are just functions. A linear transformation is a function. It has inputs and outputs. I've got the picture kind of over here to illustrate. You've got arrows going from the left side to the right side. It's just inputs and outputs. We have this extra little thing that the function has to respect addition and scalar multiplication. But aside from that, it's basically just inputs and outputs. So we draw these arrows to kind of show that. Now in the videos, the first video that you would have watched last week, I had a video about the kernel of T, and then I had another one about the range of T. So I just want to briefly remind you about these things. In red over here is the kernel of T. And can everybody see this okay? Picture? So what I'm doing here on the red side, I hope the red is showing up. All of the arrows coming out of this red circle are getting sent to 0. That's the kernel of T, right? It's those vectors that get killed by the transformation. So T of V equals 0. So that's this red circle here, all the arrows going to 0. That is always a subspace of V. If it's a subspace, guess what? I'm going to be asking you to find a basis and find the dimension. Those kind of things are natural follow-up questions. So we can talk about the subspace consisting of the kernel of T. Now on the right-hand side, we have the range of T. The range of T is just the part of W where you have arrows coming into it. You see? So remember, guys, W is the big universe. It's the big vector space on the right-hand side. We're not saying that everything in W necessarily is an output of the function. I mean, you guys have seen many examples of this. Just go back to, calculus. Just go back to x squared. All right, here's a function, f of x equals x squared. And I would view that as a function from R to R. But we're not saying that everything in this R is actually an output. In fact, if you take a look at it, the only outputs that we get out of this x squared function are the positive numbers, right? You never get a negative number as an output of this function. So there can be vectors up here, right, in W, way up here somewhere, that don't have any arrows coming into them. That would be like these points down here. There's no value of x that's going to give me those outputs. Okay. So it's certainly possible that the range of T might be smaller than the whole W. But it is going to be a subspace of W. What is it? It's the set of all of the outputs, the set of T of V, right? But when somebody asks you to compute the range of T, you're not going to want to like transform every vector. Instead, I've got this thing with the black star next to it. That's the line you want to know. That's the one you're going to want to use, which is you're going to take the span. Oh, span means subspace, right? If it's a span, it's already a subspace. We know that. And span of what? Well, I'm going to transform, let's see, T of V1, T of V2, T of V3, and so on. where these V's are a basis for V. Okay, so we're gonna grab a basis for V and just transform those vectors. That's what we're gonna do. Doesn't matter which basis we use. Well, it shouldn't make a difference as to what the range of T ultimately is. But if 10 different people choose 10 different bases to start with, they might get a list of 10 different outputs here. But it doesn't mean that it's a different range of T. It just means that you have a different list, but by the time you take the span, right, by the time you throw in all possible linear combinations of those vectors, well, at that point, you and the other 10 people in the room who may have used a different basis should ultimately have the same final answer as to what the range is. Does that make sense? This is one of the tricky things about this class is that when you're talking about a basis, there's not just one right answer. Can't check in the back of the book because the back of the book only has one answer. You might have a different answer. The person next to you might have a different answer, right? Because you can always choose whatever basis you want, and there can be lots of good choices. So we're gonna see that a little bit today as well. Okay, so far so good. Are there any questions on what I've said so far? We're gonna practice on this group work. Did you guys have a little good luck with the group work, or was it kind of eh? We're gonna go through it. We're actually gonna go through it. I'm gonna make sure that everybody is totally solid on those two problems. Before I get to that though, there's a couple more things on the board over here I want to mention. The first one is that although the kernel is over here on the left side and the range is over here on the right side, and they look like they maybe have nothing to do with each other, they actually do have a connection. And the connection is in the sizes of those subspaces, right? The dimension of the kernel, this is called the general rank nullity theorem. It's one of the things in the video that you guys watch. The dimension of the kernel plus the dimension of the range adds up to the dimension of V, right? Okay. Why is that helpful? Why is it good to know that? Well, usually you're going to know what the dimension of V is, right? That's just the, this is V, right? This is V. We know the dimensions of these spaces. So the other two numbers play off of each other to add up to the dimension of V, you see? So if you know the dimension of the kernel, then you can find the dimension of the range. Or if you know the dimension of the range, you can find the dimension of the kernel. It works both ways. That's the power of that formula. This box down here, we're going to look at this a lot today. We're going to leverage that to help us out a lot with what we're doing today. Okay. So there is a connection there. Finally, I have a couple of definitions up here. These are just the ideas of one-to-one and onto. The last video that you watched, I kind of talked about this a little bit. A one-to-one transformation is just a transformation where the kernel is zero. It's just a word, it's just a definition. So if the kernel comes out to be just zero, tiny kernel, then T is called one-to-one. On the other hand, if the range of T is the whole entire W, right? Then we're going to say that T is onto. So that would be the situation where everything in this whole blue thing was actually the whole W, right? In that case, T is called onto. And it's possible that T could be both. T could be both one-to-one and onto, in which case we call it an isomorphism. So it's a fancy word, and we're going to see examples of isomorphisms today as well to talk a little bit more about that. Yeah, Nathan.
Does one-to-one mean that every vector in V has only one unique output in W?
Does every vector in V only have one unique output in W? That's actually just the definition of a function. A function, you plug in a vector into a function, you are not allowed to output two different. It's like you plug me into a function, and want to spit out social security numbers, you cannot spit out two social security numbers for one person. That's just not even a function to begin with, right? So, but what it means, what it does mean is that you cannot have two different inputs going to the same output.
And how about the kernel?
So if the kernel is not 0, then you're going to have multiple different arrows coming into 0, right? That would be like if you and me and every 5 people in this room all had the same social security number. This would not be one-to-one.
So it's not a function at all then.
Well, it would be a function. What I've drawn here is a function. Right, it would be fine to assign me the social security number 1, 2, 3, 4, 5, and you the social security number 1, 2, 3, 4, 5. It's okay, but that's not a one-to-one function. If I have two different inputs
No, that's not.
going to the same output. But honestly, for our purposes, guys, this is the definition that you need to think about. And if you've calculated the kernel and the range, you'll know whether it's one-to-one or onto just from that information. So in other words, like part D here in this second problem is literally just a follow-up. After I figured out the kernel and the range, I'm going to be able to answer this in 2 seconds. It's not going to take much. Okay. So that's a quick summary of what was in those videos. Does anybody have any questions on that so far? So good. Okay, let's take a minute and talk through these group work problems. This is really a chance to see the power of the general rank nullity theorem and just practice how to find kernels and ranges. So that's something I want everybody to be able to do. Okay, so let's look at this first problem here. We have a transformation from sorry, there was one more thing I need to write down. Let me come over to the other board here to do this. I think this was also in my videos, but I forgot to put it in the recap. So I'm just going to remind you about 3 facts. And these are really, really helpful for answering questions like the one on number 1 over there, because there's a quick way to kind of narrow down the choices here. So if the dimension of V is bigger than the dimension of W, so you've got the V and the W, right? The inputs and outputs. If V is bigger than W, then I don't even care what T is, what the formula is. I can already tell you that if V is bigger than W, then T cannot be one-to-one. Now, it might be onto. That would require a little bit more investigation. It might be onto, but it cannot. There's no way that it can be one-to-one if V is bigger than W. On the other hand, second fact, if the dimension of V is less than the dimension of W. Okay, so if V is smaller than W, in this case, then T cannot be onto. Cannot be onto, and it might be one-to-one. Does this sort of analysis sound familiar?
Yeah.
If you go back to chapter 4, when I would give you a set of vectors and I would ask you, are they a spanning set? Are they linearly independent? Are they both? Are they neither? Right? We could do some kind of a numerical comparison. I think we were using K and N at the time, and we could kind of make some kind of conclusions that are like this. So this is just a Groundhog Day. We're revisiting these sort of three possible scenarios here. The third one, not a surprise, right? If the dimension of V equals the dimension of W, then can somebody remind me what are my choices over here?
Both or neither.
Right, T is both or neither, exactly. So T is both or neither. Okay, so we're going to try and take advantage of this to help us with analyzing some of these problems here. Yeah,
And for the third one, is there an easy way? Because like last time we did use determinants, if determinant equals 0, right? For here,
there is a similar easy way that you can do. So we'll get into, I'll show you some examples just in just a little bit. But yeah, there are some nice shortcuts on that. Okay. Any questions so far on anything on the recap or what I just went through over here? Are we feeling pretty good about this? This is all right, like really big stuff that I want everybody to know pretty well. Let's play with it. Let's look at these examples here then. The first one, I'm going to give you a transformation from R4, and this is from the group work number 10, by the way. Okay. From R4 to the 2x2 symmetric matrices. Now, the first thing about this is that I always like to do is figure out the dimension of V and W, because I want to use my facts over here. So if I look at that, the dimension of, what is the dimension of R4? 4, right? I'm just going to write that one. I'm just going to put a 4 right there. Okay, so the dimension is 4. And here's the tricky one. And a few people got caught on my midterm with this. You see the words 2x2 matrices, and you're thinking, oh, that's also 4-dimensional. But remember that if there's a constraint or there's some additional conditions that are in place, the dimension can actually go down. Right? Does anybody know what the dimension? This is kind of like my W right here. Does anybody know what the dimension of that is? Somebody different? Yeah. It's only 3. It's actually only 3. Exactly. It's 3. And the reason that it's 3 is if I actually write down the form of a 2x2 symmetric matrix, ask yourself, how many different letters do I need to use? Well, for a symmetric matrix, you probably remember that the off-diagonal entries have to be the same. Right? So in terms of the form of the vector, right? The form of a 2x2 symmetric matrix is like this. So when you bust out the variables, there's only 3 variables to bust out. And so this dimension is only 3. It's only 3. So I've got 4 and 3. Let's take a look. So that means that we're in what? The first case, right? If the dimension of V is bigger than the dimension of W, then T cannot be 1-to-1. I'm going to cross it off. If it's not 1-to-1, then it's also definitely not both. So we just have to decide now whether it's onto. And to figure out whether T is onto, I just need to find the range and see if it's equal to the whole W here. Okay, so let's talk about that. So let's do, for the solution, I'm going to focus on the range of T. Now we have a formula over here. I'm going to try to keep it up here today. The range of T is the span of a transformation of a basis. Let's write that down. The range of T is the span of the transformation of, so we have to choose a basis now for R4 that we want to work with.
Standard basis.
Yeah, any basis is okay. You can choose a crazy basis if you want to. But why do that, right? We may as well make things easy on ourselves. Let's just choose a basis for R4 that is as nice as possible. How about 1, 0, 0, 0? And then I'm going to transform 0, 1, 0, 0. And then I'm going to transform 0, 0, 1, 0. And then I'm going to transform 0, 0, 0, 1. So again, where is this coming from? This is coming from me choosing a basis for R4. Everybody in this room could choose a different one, right? This is just one choice. This is just my choice for a basis for R4. Okay, so now we're just going to plug it in. We've got the equation here. Let's just plug this in. We're going to get the span of. So the first, so what is this? T of 1, 0, 0, 0. I'm going to put a 1 for the A and a 0 everywhere else. So I just see an A right here, right? So I have a 1 down there in the lower right corner, but there's no other A's anywhere in that matrix. So that's just going to give me 0, 0, 0, 1. okay? Slow me down if I'm going too fast. I want to make sure everybody's got to be able to do this. The second vector, I'm going to put a 1 everywhere I see a B in the matrix on the right side. So there's a 1, there's a B here, 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 and a minus B right here. So when I plug that in, I'm going to get a 1, a 1, a 1, and a negative 1. I'm just ignoring the A, C, and D and just plugging a 1 for B. Okay. Look okay? Great. And then the next one is 0, 0, 1, 0. So now I'm going to put a 1 for C. And I'm going to pick up those coefficients that are in front of the C. So I get 1, negative 2, negative 2, and 1. Finally, I'm going to put a 1 for the D variable. What matrix am I going to get when I put a 1 for the D variable?
All zeros.
All zeros, right? There's no D's anywhere over here. Okay. Okay, guys, so now you ready for something really important? Is this a basis for the range of T?
Not yet.
We got to be careful about that, right? We got to be careful. Over here, yes, there are n vectors in this list. It doesn't mean the range is n dimensional. What could go wrong?
Linear dependence.
The vectors might be linearly dependent. And in fact, I can already see that I spent at least $1,000 too much already, right? This vector here is never going to be in a basis, right? We're going to want to get rid of that guy for sure. So actually what we can do is we can do our linear independence check. So it's a good day to review. It's been 2 weeks off. Review what we learned back in chapter 4, right? So we put these vectors into the columns of a matrix. So the first matrix, I'm going to write it as a column right here. Yeah, the second matrix, 1, 1, 1, negative 1, that goes in the second column. Then the third column is 1, negative 2, 1. And then I'm going to just get rid of this one already, okay, because I know I don't want that one in there. But let's just check whether these 3 are Li. So this third matrix, I put it in the third column here. Okay, so you just load up those columns with those vectors. Now you got to do EROs, and I'm just going to basically tell you, you can move the bottom row to the top, right? So I'll do that. There's a pivot right there. Notice the second and third rows are the same. So let's just cross one of them off because they're just redundant basically. Then I'm going to just write down the second row here, 0, 1, 1, 0, and then I have 0, 1, negative 2, 0, and so on. All right, so I'm going to get a pivot right here. I'm going kind of quickly because this is just the boring ERO stuff. But basically what's going to happen, I'll just do one more step. You are in fact going to get a pivot in every column here. So this will eventually become a 0, 0, 1, 0 in the third row. So I'm not showing all of my work, and I'm certainly not explaining and spending a lot of time on that. I just want to get to the row echelon form, which is basically this matrix right here. And I've circled my pivots. And so this is a check. This is a yes on Li. And when I say yes on Li, I mean for these 3 matrices, right? Now, here's the thing, guys. They're Li. What's the other thing they have to be in order to be a spanning set, in order to be a basis? A spanning set, right? Now, here's the thing, guys. They are automatically a spanning set. Because what is the range of T? By its very definition, it's the span of those vectors. A set of vectors always spans whatever they span. So they are definitely a spanning set for the range of T. And because we checked that they're also Li, then that makes them a basis, right? So I need to write this somewhere. Let's just come up here. I think I can squeeze this in. A basis or the range of T. This is the kind of thing that, these are the kind of questions that we get asked in this section. Find a basis for the kernel, find a basis for the range. So here we go, we have that matrix, and then the second matrix, and then the third matrix. We already got rid of the fourth matrix, which was just the zero vector. So there's your basis right there. Okay. Can somebody tell me then whether this is onto? We've crossed off one-to-one, we've crossed off both. We're trying to decide if it's onto or not. What do you think?
Yes, since the dimension of range is equal to the dimension of W.
Perfect, beautiful, absolutely right. This is a three-dimensional range. And look at W. W was three-dimensional, right? So the range and the W have the same size, so they're actually the same. Exactly, so let's write that down as well. So the correct answer here, guys, it is onto. I'll circle onto now. And I'm just going to note, I'll do this right over here if that's all right. Can you guys all see right here? You see this okay? Okay, so what I'm going to just say is that the range of T equals W. I'm sorry, this is W here. This thing, if anybody's wondering what is W, this is my W. The 2x2 symmetric matrix. Range of T equals W, so T is onto. So T is onto. Does that make sense? Let's just play the numbers game for a minute over here. I've got the dimension of V is 4, right? That was the input side. We just figured out that the range is three-dimensional. So what is the dimension of the kernel on this example? It is 1, right? Because 1 plus 3 adds up to 4 here. Well, that means it's not one. That confirms that it's not one-to-one. Right? One-to-one would be if the kernel was zero-dimensional. So it's not one-to-one. This one is onto, but not one-to-one. That make sense? I have a crazy question for you for a minute. I want you guys to think about this for a second. Let's suppose that you think that you're not very good at finding ranges. You're just not that good at it. You don't like it. You don't like the range of T. It's not a concept that is your friend. Could you still answer this question about whether it's onto?
Yeah.
How?
Using kernel, finding the kernel, and using the ring pulling theorem.
Boom, exactly right. If let's say I don't want to deal with the range at all, this equation tells me that, okay, that's fine. If you can figure out the kernel instead and find out that that's a 1, then through the back door, you'll figure out what the range is. And it'll be three-dimensional, which means it equals W, and so T is onto. Isn't that great? So you can play this equation to your strengths, right? Play to, stay away from your weaknesses and play towards your strengths. If you're really good with kernels, find the kernels. If you're really good with range, find the range. And then you can use that equation to sort of work things the other way around. I like that a lot about this section. Yeah, and?
Would you technically give us full credit for using that backdoor?
I would not only give you full credit, I would be grading with a smile on my face. It's like, yes, they're using the general rank nullity theorem and they're realizing the connection there. So yes, absolutely, it's a good thing to keep in mind. For sure. Any other questions on this example? Really?
I'm a bit confused on how the range T equals W. Is the range T just because you count 3 vectors right there? Or
Yes, I have 3 vectors here. So that means that the range of T is three-dimensional. That's like how big it is. It's got 3 things in it. But at the same time, W is also three-dimensional. It's because the W and the range of T are the same size, it actually means that this blue circle is the whole same size as W. It fills the whole space. It's not just inside of W, it is W. That's the point. Does that make sense? Everybody feel okay with this? All right, fantastic. Let me move my camera over here. Let's take a look at this second example. This is a little bit review of some things we did before spring break here, but I just thought it would be good to practice a little bit more. Let's suppose that T is a transformation from P2 of R to M2 of R. So can we get the dimensions up here for me? What's the dimension of P2 of R? 3, right? It's 3, great. I see a lot of folks say 3. How about the dimension of M2 of R? 4, right? It's 4-dimensional. Great. So let's check out our little facts over here. If V is less than W, then T cannot be onto. Let's cross off. I'm going to come down to this question, right? I'm going to cross off onto. It cannot be onto. And so it's maybe 1-to-1. And otherwise it would be neither. Okay, so we'll come back to the rest of this. We can't answer this immediately. The 1-to-1 part, I cannot answer that immediately. I can cross off the 2 wrong answers, but I still have a little more work to do here. Okay. Well, let's go back to part A. It says find T of ax squared plus bx plus c. Anybody have a suggestion? So they gave us T of 1, they gave us T of x plus 1, and they gave us T of x squared plus x plus 1. We've seen problems like this before. Actually, I think there was one on the test, right? On the exam, I had an example kind of like this. What do we need to do here, Nathan?
So first, we're going to get transformation of x squared by subtracting x squared plus x plus 1 minus transformation of x plus 1.
Okay, so if you subtract these two, right? If I take this one minus this one, notice what we have here, x squared plus x plus 1, and here I have x plus 1. If I subtract those, I just get x squared. And T respects that subtraction. So I can take this matrix minus this matrix. Yeah.
You can go the other way too, right? You can do like T of x plus 1 minus T of 1 and then square it.
Oh, you can't square anything.
Or you can't square it.
No, because when you square something, it's like multiplying. And in a vector space, all we can ever do is addition and scalar multiplication, which also includes subtraction, because subtraction really is addition. But yeah, we can't actually square anything here. But I like what you're saying, because we actually do want to subtract these two just to get T of x.
Yeah.
Right. So in fact, let me start right here with this solution. I'm going to use the fact right here, guys. This is the first step. I'm going to use the fact that T respects linear combinations. Right, I know that it respects those linear combinations, so I can go ahead from the beginning and write that down as a linear combination. So the A comes out in front and the B and the C. And like we've been saying, so I already know this last term because T of 1 was given to me over here. The matrix on the far right side is already in place. But they did not tell me T of x, right? So this is where I'm going to use the idea, Dylan's idea of subtracting these two vectors, right? So I'll take this matrix minus this matrix. So let's just put that right here. Just doing slot by slot subtraction. -3 minus -1 is actually -2. 0 minus 2 is -2. 2 minus 0 is 2. And 1 minus 0 is 1. So that's the B term. And then, as Nathan suggested, we need to figure out T of x squared. So just again, a quick word of caution. We cannot just square this matrix. Instead, what we have to do is come over here and take this third matrix minus the second matrix. 3 minus -3 is actually 6. -2 minus 0 is -2. 0 minus 2 is -2. And 1 minus 1 is 0. So this is the idea. And, now, this could, oh, I need a plus sign here. Plus sign in between those terms. This is basically a final answer. But if you want, and I actually do want to do this here, I'm going to compress this into a single matrix. So if I just like go across the upper left corner of all of the expressions here, see I have 6a, -2b, and -c, that's all in the upper left corner. So 6a minus 2b minus c. just in the upper left corner. And then in the upper right corner, we have what? Negative 2a minus 2b plus 2c. Okay. And then in the lower left corner, I have negative 2a plus 2b. And in the lower right corner, I just have b. This is what we should have for the first part. So far, this is just figuring out the transformation, what the formula is based on what was given to us to start with. So far, so good? Makes sense? Okay, so then in the second part of the question, which is on the group work, it's parts B and C. They want to know what are the bases for the kernel and the range. We can start wherever we want. If we feel good about ranges, we can start with that and then try to find the kernel second. Or we can start with the kernel and then find the range. We can play this game to our strengths, right? We'll figure out what we want to start with. Because I did the range over here on the first example, I think I'm going to start with the kernel on this one just to mix it up a little bit, but we could start anywhere really. Yes, Sebastian?
Since we determined that it's not onto and it might be one-to-one, would it make sense to start with the kernel anyways, since that would determine whether it's one-to-one?
It would, except that as I was talking about on this example, if we started with the range and we figured out what this number was, we could then use the equation to figure out what this number is. So we would be able to answer the one-to-one question through the use of that equation. So we can actually do it either way. But you're perfectly right. I mean, there's no reason not to just start with the kernel if that's what you're interested in here. So let's do the kernel. Let's start with the kernel if that's good. Am I going too fast for anybody? So far, so good? Okay, great. So let's do the kernel. Kernel of T. Now, how do you find the kernel? Well, that's over here in the red writing. T of B, we're going to set it equal to 0, right? So we're going to take, I'm going to take the matrix there, 6a minus 2b minus c, negative 2a minus 2b plus 2c, negative 2a plus 2b, and b. And just going to set that all equal to 0. Now, my goal is to solve for the polynomial, right? The a, b, and c essentially. This actually creates 4 equations because there are 4 corners in the matrix and they have to match up on the left side and the right side. So for example, I know that 6a minus 2b minus c, that has to be 0. And then in the upper right corner, negative 2a minus 2b plus 2c, that has to be 0. Lower left corner, negative 2a plus 2b, that has to be 0. And in the lower right corner, b has to be 0. So yeah, this is a system that, you could put this into a full-blown, augmented matrix now and solve it with EROs and so on, but I'm going to sidestep all of that and go a lot faster if you don't mind. So you can just look at this one. Because if you start at the bottom, b is already 0. And then using that in the previous equation, we find out that a is therefore also 0. And if b and a are both 0, well, then you can figure out that c is actually also 0. So a, b, and c, they are all 0. I'll save you the agony of EROs for that. We'll just kind of figure that one out by inspection.
One-to-one.
Yeah, so what you're seeing here then is that your kernel of T, right? So remember the kernel, now this has to be a polynomial here. It's an infinite. But if A is 0 and B is 0 and C is 0, then you don't have anything, right? You have basically 0. It's just literally 0. The kernel is 0, and that's exactly what one-to-one means. Okay, so T is 1-to-1. And I'm going to actually answer part D right now. T is 1-to-1. We can circle that We already know that that's the correct answer. Great, so it's 1 to 1. Is everybody with me? Sense? Now, a problem like this, we already know that the transformation is not onto, but they're still asking us to find a basis for the range. So we should do that, right? We should be fully comprehensive in our solution. So I am going to look at that. Oh, I should mention, by the way, if the kernel is 0, then what is the basis for the kernel?
Nothing, 0.
It's nothing, basically. There is no basis. In fact, you could say, I mean, the dimension is 0, which means that there are no vectors in the basis. So it's a little bit of a trick question, find a basis for the kernel. Well, there isn't one. This is a 0-dimensional space. Okay, but let's take a look at the range. Now, the range of T is the span of the transformation. It's over here in the black star, right? It's the span of the transformation of
Basis.
any basis for V whatsoever. Here is V right here. And Jesus, what's your favorite basis for P2 of R?
That's that 3, right?
Yeah, so I want to have 3, if I want to have 3 basis vectors, what might you think of using? Just for 3 polynomials, basically, that we're talking about P2 of R, the 3 specific polynomials.
Where we start with x squared.
Okay, so we can do x squared, and we're going to do T of x squared. And what's the next vector that you like? X, I like it, okay, and then what's the next one?
It's a variable, or can it be any other?
I need a specific polynomial. It needs to be a basis, so I don't want to like create any linear dependencies here. But what would so if I start with x squared and then I do x, can somebody help them out? What comes next? Yeah?
T of 1.
T of 1. Yeah, it's just T of 1. So we basically just going to do T of 1 right there. Okay, yeah, that's kind of like the standard basis for P2 of R. Now, this is not the only basis. Right? We can use any basis. Actually, let's imagine with me for a minute, guys, that we had not done this work here yet. Then would there maybe be a different basis that would have made more sense if I had not done this work in blue and the only information I had was the black stuff? Would there have been maybe a different basis for P2 of R that would have, been less work for us to start off with? Carson? Not sure? Anybody have an idea? Because remember, any basis is okay. Sebastian?
Sort of the default basis of the 1 0 0 0 0 1 0 0.
Okay, it can't be matrices though.
Oh, it's not.
We've got to have a basis for P2 of R.
Oh, E2, okay.
Yeah, so we're looking for polynomials. Because this is a basis for V. But is there a default? So this is the one I always think of. Right, the one that Jesus has right here. This is the standard basis for P2 of R. But would there have been another basis that we could have used because of what was given? Take a look right here, guys. Yeah, 1 and x plus 1 and x squared plus x plus 1. That's a perfectly good basis for P2 of R. And why is it such a easy choice? Is because what am I supposed to do? I'm supposed to transform the basis vectors. Well, they already did that for us. We already have the 3 matrices that we're supposed to get. So we can just literally write them down. You see what I mean? So I just wanted to make that point that sometimes, although this may seem like the go-to basis that you would always use, there might be situations where based on the information that you have, a different basis might make more sense. So what I'm going to do, maybe it'll help when I write down the next step as to what we're actually doing here. I'm going to do T of x squared. What was it? That was this one right here, right? So that's simply 6, -2, -2, 0, comma. And then T of X is the middle matrix here. -2, -2, 2, and 1. And then the third big vector, which was T of 1, is -1, 2, 0, and 0. With me? Now again, if you had decided to use these three basis vectors here, what would you have said the answer was? You would have used span of -1, 2, 0, 0, and then you would have had -3, 0. You don't have to write all this down. I'm just trying to make a quick point here. Right? This would also have been correct. These three matrices are not the same as these three matrices, but their spans are. By the time you take all possible linear combinations of these three matrices, what you'll have in your hands is the same thing as if you take all possible linear combinations of these matrices. That's the thing. This is why we have, 30 people here. We can have 30 different right answers. Because the minute you throw the word span in front of it, this is just making sure people know what the span means. You're taking all possible linear combinations of whatever you started from. Okay. So that's basically what we're saying is the actual matrices can be different. Okay, guys, this is going to get even better now. This is going to get even better because what's the question say? It says find a basis for the range of T. Is this a basis for the range of T?
I think it is.
It's definitely a spanning set. Because by definition, the range is just the span of these vectors. But what else do I need to check?
LD.
To have a basis, what are the requirements? Has to be a spanning set. Everybody with me on this? Has to be a spanning set, and what's the other thing? Li, right? It has to be linearly independent. In fact, we checked it over here, didn't we? But you know what? I don't have to check this one. Why not?
Has 0.
Because it must be, because we have the numbers over here. This was 3, right? The dimension of V was 3, and didn't we already do the kernel? What did we say here? The kernel was 0. So we know that this is a 0. So when you think about the range, what is the dimension of the range? I know it has to be 3-dimensional. If these vectors were LD, you'd be throwing some of them away, right? We'd be going back for a refund and we wouldn't have as big of a range. We know that this has to be Li. So let's write that down. These must be, we don't have to do the Li check. We can just say that they are Li. These must be Li since the dimension of the range of T is 3 from the general rank nullity theorem. That is a really, really nice theorem, isn't it? So that general rank nullity theorem tells me that the dimension has to be 3. So these vectors have to be Li. Isn't that incredible? That we somehow are now doing Li checks by using the theorem with the numbers in it over there. We managed to somehow use the theory, like the power of linear transformations is the relationship between different vector spaces that these transformations are making. And it's allowing us to figure things out that we couldn't have done a few weeks ago. A few weeks ago, if I ask you, is this a basis? You're going to throw them into the columns of a matrix, do the EROs, and follow the pivots, right? That's the only thing we have. Well, now all of a sudden we have this beautiful theorem with numbers over here. We say, oh, we already know what the dimension is supposed to be. So here we go. We have exactly the right number of vectors So they've got to be the basis then. Exactly, so they must be Li since the dimension is 3 from the general rank nullity theorem. Hence, these three matrices are a basis for the range of T. I just want to be real clear, they're not a basis for W. Don't get things confused with the W here. The W is 4-dimensional. M2 of R, that's a bigger universe, right? That's the huge W. We don't have a basis for that. What we have here is a basis for the range of T. Does that make sense? Yeah, Jesus?
So if the dimension of V was equal to 2, you would know, or
If this was a 2, and we'd already done the kernel here, then you would actually know that the dimension of the range would be 2. And that would mean we would know that these are LD, and then we'd have to throw something away. Exactly.
and then we would just figure out which one we have to.
Which one to throw away, and we can do that in one of two ways. You can either put them in the columns of the matrix and figure out which column is unpivoted to get rid of that vector. Or you could just throw something away and just make sure that the two things you're left with are not multiples of each other. That's a kind of a simpler way in this case. Yeah. All right. Does that make sense? Now, again, you know, what you've noticed here, guys, is that by doing the work on the kernel here, we made our life very easy over here. If we had done this the other way around, let's suppose that we had not done this work yet. Let's say we didn't know yet that the kernel was 0. If we didn't know that the kernel was 0, then I would not know that these are Li. I would have to check it. So I would check it, I find out that yes, they are Li, and then I would be able to come over here and do this part really easily. Right? If I knew that this was a 3, then I would know that this is a 0. You see? So you have to do hard work either here or here, but not in both places. And so if you're really, really good at kernels, then you can do this work and get it easy out over here. But if you're really good at doing ranges, then you can work on this part, get the basis for the range over here, and then have an easy out over here. You see, it's kind of how you want to play the game, right? You play to your strengths, and you can really make this a little bit easier. Okay. Any questions about that? Any comments or questions? Ant, yes.
Real quick, so how would it look like if it was to be chosen as neither?
If it was neither, it would have to be, I mean, there's lots of examples of that. For example, so this one is already not 1-to-1. Let's just say I changed my W to be all of M2 of R, right? Well, now this is both or neither. So I use it to say I use the same formula. Right, so now this one is both or neither because I have a 4 and a 4. So if V and W are the same size, it's either both or neither. But since it's not 1-to-1, we check that it's not 1-to-1 somehow. Oh, that was because of the dimension.
Yeah.
Okay. Well, imagine you check that it's not 1-to-1. Okay, then you would know that it's also not onto. Yeah. So this would be an example of that. All I did here to cheat really is I just made W larger so that it's no longer onto. Yeah, that's kind of the idea there. Okay, any other comments about this? Before we take a break, I want to spend 5 minutes, maybe 10 at the most, to say a quick word about why we care about this. I mean, after all, these are just words over here. 1-to-1 and onto, these are just words. Like, who cares? I mean, what's the big deal if it's 1-to-1, if it's onto, whatever. Well, the word up here that's really the most important is actually the third one which is this concept of an isomorphism. When two vector spaces are isomorphic, in other words, when there's an isomorphism, a one-to-one and onto transformation between them, then those two vector spaces are extremely similar. Let me write down an example to show you what I mean by that. So just one more example. Now, this is not from the group work. This is just an extra. A quick example. I can show you, for example, that if I make a transformation, well, let's just do R4 to M2 of R via, I'll give you the equation here that I'm going to use. The equation I'm going to use is T of A, B, C, D equals, okay, can somebody think, or maybe instead of me just spilling the beans here, can somebody think of how I could fill out this matrix in such a way that it is one-to-one and onto? In other words, that in such a way that it is an isomorphism. Can you think of a way to fill it? And I'm looking for something that's very, very fast and easy. Yeah, Matt.
Like literally just put A, B, C, D.
You got it. Absolutely. Is that what you guys were thinking? Exactly. We just fill this out in kind of like the no-brainer way of like making a transformation. Okay, and I will let you take my word for it that this is one-to-one. If you set it equal to 0, then you'll find out that A, B, C, and D are all 0. And it is onto, well, it has to be either both or neither because of the 4 and the 4, right? They're both 4-dimensional. This one is both. So this is an isomorphism. So this is an isomorphism. So I want to get back to the point I was trying to make is who cares? Okay, so what's the big deal about this? When you have two vector spaces in an isomorphism like this, you know what I can actually tell you is that those vector spaces, at least from a mathematician's perspective, are basically the same. They are basically the same. And what I mean by that is all of the algebra that you would do, let's imagine that I go home right now and I write out 7 pages of scratch work involving vectors in R4 written as a row. So I do it, and I'm only going to do vector space operations. So I'm going to do addition and scalar multiplication with row vectors having 4 slots. And I go home and I write out 7 pages of scribbles of calculations of row vectors using addition and scalar multiplication. Do you guys think that you could take my scratch paper and rewrite it using 2x2 matrices instead?
Wait, what?
So let's say I go home and I do something like this. 2, 3, 5, 7 minus 3 times 1, 1, 8, 2. Right? And you see that on my scratch paper. Would you be able to take that scratch paper home and redo it using matrices, 2x2 matrices instead of row vectors of 4? You absolutely would. Because all you would have to do is say, ooh, every time I see an A, B, C, D written like this, I'm going to re-express it into a block of numbers in a 2x2 format. But the algebra works the same. If I do this calculation here, you'll get the same thing as if I do this calculation here in a matrix format. It's literally just, how are you presenting the vectors? Are you presenting them as a row? Or are you presenting them as a 2x2 block? But the math is basically the same. You see that? Let me give you another one. Let me give you another example of this. What about, here's another example. Oh, I just love this. This is a beautiful idea here, right? Okay, here's another example. T, let's just go from R6 to P5 of R. And I'm just going to define this one. Okay, so I'm going to take 6 numbers, A, B, C, D, E, F. and I'm going to spin out a polynomial of degree 5 or less. Can you tell me how I could do that? Somebody, I haven't heard. How can I take these 6 numbers and now write out a polynomial on this side? Is there a natural way to do it? Go ahead.
Which the x will fit, and then all the way down to +1, so
Okay, so but I'm gonna have to use the ABCD. I'm gonna have to use these letters.
Of ax to the sixth plus bx to the fifth plus cx to the fourth plus bx to the third plus
Keep going.
bx. Wait, wait, going plus bx to the second plus f or f times x
I don't,
plus
wait,
Ooh,
no.
h.
we don't have an A. We ran out of letters. What's the problem?
just there, the x.
Yeah, there's no, in P5 of ours, yeah, we have to actually start with x to the fifth. But you have totally the right idea. I just wanted to see how that train wreck ended. Sorry, that was low blow there. Yeah, so anyway, yeah, so this is the natural answer, isn't it? Right? So you can actually take a polynomial. So if you start adding and subtracting polynomials like this, isn't it gonna work out the same as if I just add and subtract the slots like this? I sometimes give you guys a hard time. I see sometimes on your exams that people will start writing polynomials as slots. And I'll kind of ding you for it as, oh, this isn't really a polynomial if you write it like this. But honestly, actually, you're right. It basically is the same thing. This thing just translates into this thing. It's a matter of how you write it. But the algebra, the vector space workings of R6 are the same as the vector space workings of P5 of R. This is an isomorphism. Absolutely. So when you have an isomorphism, guys, what you're really saying is that your two vector spaces, they may not be presented the same way. The vectors don't look the same, but the spaces are basically the same. Why is that such a powerful idea? Well, because it basically means that if you are a genius at how Rn works, then you are very, very good at any vector space. Because any vector space has a dimension. And you can create an isomorphism from that vector space to R whatever. Right? What if I had, I don't know, let's take something, M4 of R. What would I be able to make an isomorphism to that involves R to a power? Which power would it be?
16.
16, right? And how do you get 16? It's just the dimension of this guy, right? Well, guess what, guys? There's gonna be, okay, I can write down 16 letters here. You don't need to write all this out. Did you get the idea? I write it out as a 4x4 block and I send it over here to 16 letters. And that is an isomorphism again. So you can create this dictionary for yourself. Let's say you hate polynomials. I happen to love polynomials, but let's say you hate polynomials. What could you do? You could say, well, instead of writing polynomials, I'm going to change them into slots. Because this is a one-to-one onto correspondence. I can go back and forth between polynomials and slots. So if I hate polynomials, I could rewrite everything as slots. I could take that 7 pages of scratch paper of polynomials, write them as slots, do all of my work using the slot notation, and then maybe at the end I translate back to polynomials again, right? So you can basically live in this world in any vector space problem that you want. You just have to find the right value of n. And it's just a beautiful thing. So that's kind of why this is an important concept here. Yeah, and the other thing that's nice about an isomorphism, I'm just going to very briefly say a quick word and then I want to give you guys a little break here. But when you have, so this is just, I'm going to call this a remark, and you probably should write this one down. I don't, I haven't mentioned this yet, so this is just a quick little note. For an n by n matrix A, so if I take a square matrix A, then the transformation, this is going to be T that goes from Rn to Rn via T of x equals Ax. So I'm just going to remind you for a moment that you can do these things called matrix transformations, where you use a matrix to create a linear transformation. This is a transformation from Rn to Rn, and this thing might be an isomorphism. This is an isomorphism if and only if. Can anybody tell me an idea? Do you have an idea? I know you haven't had a lot of time to think this through ahead of time, but I'm wondering if anybody has a guess about what would have to be true about this matrix. Something good about a matrix that would make this actually be an onto and one-to-one transformation. You can take a guess at this one because I don't think we've talked about this. Yeah. Invertible. Invertible, that's it. That's it. That's a good thing about a matrix. Yeah, absolutely. So if the matrix is invertible, then we have an isomorphism. It's one-to-one and onto. And what I wanted to say, I guess I got away from my point a little bit here. I'm out of practice. I haven't had to teach for 2 weeks. But what I was going to say is you can reverse an isomorphism. By the way, so you notice, take a look at this example here. I'm inputting a row vector and I'm outputting a 2x2 matrix. I could reverse that. I could take the 2x2 matrix as the input and go backwards and output the row vector. Or I could take the polynomial as an input and output the 6 slots here. So I can go from left to right the way it's defined, but I can also go in reverse, right? It's called the inverse transformation. And there is an inverse transformation. In this case, one more line here, right? We have an inverse, and it's actually written as a t to the minus 1, right? T to the minus 1 takes a vector x. And does anybody have an idea? Again, I'm asking for a wild guess here. To undo the transformation T, in other words, to reverse it, to go backwards. Does anybody have a thought as to what I would want to do in this inverse transformation that I'm creating? I started with this one, and I want to do an inverse here. What I think I heard it. Take the inverse of A exactly and multiply that by x, because that will undo, very good. That will undo the original transformation. So it's pretty sensible. It makes sense that that's what you would do. You will see that on the homework for Monday. So I just thought I would mention that. You'll actually have to take the inverse of a matrix and use that to write down the transformation. Okay, guys, this has been great. Are there any questions at all here?
Does that mean that you can kind of go backwards if you find out a matrix is invertible, then you can find out that it's an isomorphism?
That's right. Yeah, you can add, if I start off knowing that I have an invertible matrix, in fact, I've tried to draw this as a double arrow to point that out. Yeah, if I start off with an invertible matrix, then I can make this transformation into an automatic isomorphism by just defining this way. That's exactly right. Excellent point. Great. Any other thoughts or comments on this? Okay, we're going to take a 10-minute break. When we come back at about 3:25, we're going to start chapter 7, and it's a whole new can of worms. So I will see you all back in about 10 minutes. I would tell you to go out and get some fresh air, but I have a feeling it's pretty hot out there. This thing center here. I feel like it's somewhat cool in here, but it's not great.
Yeah.
Little bit questionable. Anyway. I feel myself losing my voice. That's usually what happens on like the first day of the semester. When I haven't been using my voice that much. I'm just have to get my throat back into teaching mode for another month. But all right. Well, I think we got most of the crew back. I'm gonna go ahead and let you guys know. So we are covering 9 chapters this semester, and we are now done with the first 6 of those. I kind of said we're at about the 1/3 mark to go. And chapter 7 is the last chapter until we go back to differential equations. So we just need a little bit more linear algebra. I know we've been at it for a while, but once we cover this last topic here, we will be fully equipped to go back to differential equations. And honestly, you cannot have a class on linear algebra without talking about eigenvalues and eigenvectors. So this last chapter that we're going to be covering on the linear algebra side is kind of mandatory. It's kind of a big deal. And it will also be useful when we go back to the differential equations. So you'll be seeing all of that come into play. The first thing I want to let you guys know about chapter 7 is that all of the matrices in this chapter will always be square sized. Okay, so we're going to let capital A be an n by n matrix, always a square size. Does anybody remember another place this semester where all of the matrices were square sized for the entire chapter?
Determinants.
Determinants. Remember that you only have a determinant for a square matrix. So yeah, and we're actually going to see determinants a lot in chapter 7, believe it or not. So we're talking only here about square matrices. So let me just get right down to it, guys. I'm going to give you the definition of eigenvalues and eigenvectors. Okay. So if V is not 0 in the vector space Rn. So we're looking at a vector in Rn here, right? And lambda, which is a real number, so this is called lambda, by the way. Sorry, this is a Greek letter. So we're going to be seeing a lot of this notation in chapter 7. It's called lambda. And it's pretty standard. Everybody in eigenvalue, eigenvector land tends to use that notation. And if this is such that, okay, are you guys ready? I'm going to write down the most important equation in all of chapter 7 right now. It didn't take me long, right? Here it is. A times V equals lambda times V. Right? So if we have that, please put this in a box, highlight it, really emphasize that it is the most important equation in this whole chapter. And sometimes people forget about it. So I just want to write that down. Then we call V an eigenvector with corresponding, so V is an eigenvector with corresponding eigenvalue lambda. So the V is the eigenvector and the lambda is the eigenvalue, right? So this is the terminology here, okay? V is an eigenvector, lambda is an eigenvalue. Sometimes I will put them both together. And we can call lambda v as a pair. We can just call that an eigenpair. So they are kind of a pair. They go together. They go together. You cannot have an eigenvalue without an eigenvector. You cannot have an eigenvector without an eigenvalue. They always come as a pair. Okay? Now, before I go any further with this, let me draw a picture to show you what this is really saying. You have a vector v. Let's just draw it visually here so we can kind of picture what's going on. And, so your matrix A, I'll just put this up here, I guess. Here's A, and then here's your vector v. I'm going to draw it as a column vector. So this is an n by n matrix. And we're multiplying it by a column vector, which I'm going to think of as n by 1. When I do that calculation, what size result will I end up getting?
N by 1.
Also n by 1, right? So this is n by 1, and what it is it's literally just AV, n by 1. Put a little equal sign in there. So this vector AV lives in the same universe that V itself does. They are both in Rn. They are both n by 1 columns, right? So AV, if it happens to be the case that A times V is literally just a multiple, a scalar multiple of V, that would be this kind of picture here, right? Then we have this special eigenvalue, eigenvector relationship. So what's happened is you take the vector V and you multiply it by the matrix A. It could turn the vector, it could twist it a different direction, but if it doesn't, as long as AV points in the same direction as V itself, then we have an eigenvector. And the stretch factor is what the lambda is telling us. Lambda is the stretch factor. By the way, lambda could be negative. If lambda is negative, then AV might actually turn itself the opposite direction. Or lambda could actually just be a very small fraction, in which case the vector might get contracted by the matrix, right? The vector could actually shrink. So the vector could expand, it could shrink, it could turn the other direction, but it doesn't turn. It doesn't start pointing in a different direction. That's what cannot happen.
So that means that they're parallel, they're eigenpairs?
Yeah, the vector is parallel. V is parallel to AV. That's basically what this equation says. AV is just a multiple of V. So visually, this is what's going on. Let me just show you a very quick example. Suppose that I have the matrix 2, 1, 0, 3. I just gonna do a 2 by 2 example to kind of get the point across here. And let's just take the vector to be 1, 1. A nice easy vector to play with. Then if I actually calculate A times V, let's just see what happens. We take 2, 1, 0, 3, multiply it by the column vector of 1, 1, right, or vector. So I'm mainly going to be writing, you reminded me I need to move this over here. I'm mainly going to be writing my vectors as columns here, up and down in chapter 7. Okay. So let's just do this. Can we do this matrix multiplication? 2 plus 1, that's 3. And 0 plus 3, that's 3. And what you notice is, whoa, that's just 3 times the vector that you started with, which was 1, 1. So the lambda is 3. And the V is the eigenvector 1, 1. So you just end up here with lambda V. It's just lambda V right there, and we just check that off. That works. Okay. Does that make sense? So what's happened is, if I was going to draw this, here's the vector 1, 1. That's V. Say 1, 1. The vector AV is now just 3 times longer. There's AV. It's just 3 times longer, but points in the same exact direction. Pretty simple idea. So far, so good? You probably have a lot of questions. Like, how do you find the eigenvectors? How do you find the eigenvalues? Who cares? What's the point? Right? There's a lot of things we have to get into. I've only had 5 minutes to start on this so far. We're going to get into some more of this. However, before we get into anything else, I don't normally like to get too sidetracked, but there are some things that people tend to write down that I've taught this class 35, 40 times. I mean, I do it every semester. So I've seen what some of the pitfalls are. And I just want to make a quick comment so that maybe we can keep you guys from making those same pitfalls. One pitfall that I see a lot is this one. Oh, AV equals lambda V, I'm going to cancel the V. So I see this a lot. And you end up with something that makes no sense whatsoever, because now you're trying to tell me that a matrix is equal to a number, right? So that doesn't make any sense. So all of these things that I'm saying bad, you may or may not want to write them in your notes. If you do, be sure to put a X through it or red pen or something to make sure that you don't accidentally screw this up. Okay. Another thing that I see that is illegal, right, is I see people, they look at the AV and they think, ooh, let's square both sides or something. And so they'll do something like this. And what you have to realize is that what you're doing right now is you're squaring a matrix, a vector. This is a vector, right? I don't know how to square a vector. I know how to add vectors. I know how to subtract them. I know how to do scalar multiplication, but I don't know how to take a vector and multiply it by itself. So this is no good. Don't want to be doing stuff like that. Okay. Another thing that is no good, and it's a very simple little thing, but you got to be careful about it, is I will see people getting sloppy and writing the matrix on the right side of the vector instead of the left side. This is also not making any sense, because you can't take a column here and multiply it by a matrix on the right. This is not, the sizes don't even work, right? So we don't want to be doing stuff like that. And last but not least, for people who really just don't learn the formula very well, especially after I say this is the most important formula in chapter 7, I will sometimes see people who will somehow get it mixed up, and they'll have A times lambda showing up. And that's nowhere on that board over there, right? So we want to stay away from all of these pitfalls and try to avoid anything that's over here. Okay, just wanted to get that out of my system before we go any further. So far, so good? Okay, well, I'm just gonna take a few minutes and derive how do we find these eigenpairs, right? Here I just sort of handed the vector to you, and all we had to do is run the calculation through, and we saw that it worked. But how do you actually do it from scratch? That is something worth trying to understand a little bit. So how to find eigenpairs? How do we find these eigenpairs of our matrices? Well, so it turns out that what we really are going to do is find the eigenvalues first. And once we know what the eigenvalues are that are going to show up, we can then write down the associated eigenvectors. So I'm just going to start off this way. Lambda is an eigenvalue of A if and only if I'm going to use this whole board as a kind of a theoretical derivation. Okay. So what does it take for a number lambda to be an eigenvalue? Well, it means the box over there, right? The most important equation in chapter 7. So it means that AV is equal to lambda V. This is going to be for some V not equal to 0. This is pretty much just the definition of it. Eigenvalue, lambda is an eigenvalue. I'm just reiterating what's in the box on the left side. And now I'm just going to manipulate this a little bit. I'm going to subtract everything to the left side. So AV minus lambda V equals 0. I'm also going to just do ditto symbol here. This for V not equal to 0 just gets carried. It's going to get carried all the way down. I'm going to do about 5 or 6 steps here. Okay, so give yourself a little bit of room to write all of this, all of these steps down. What is your natural instinct to do with this equation here that is now on the left side? Pull out the V, right? Now, but let's think to ourselves what's going to happen when we do that. When we pull out the V, we're going to be left with what? A minus lambda. That goes right back into the idea that A is a matrix and lambda is a number. So how can we subtract a number from a matrix? You can't really do that. It's like apples and oranges. So here's what we do. It's a simple way to get around it. We simply, sorry, I'm going to steal a little bit of room here. We simply squeeze, remember our good friend, the identity matrix? This is the IN matrix. Do you remember that? It's been a few weeks maybe since we've really seen this very much. This is the matrix, right? So I'll just remind you over here. The identity matrix, we've got ones right down the main diagonal, zeros everywhere else. The significance of that was it's like multiplied by 1. So if you fudge that into your expression here, it's like harmless. There's no problem. You can just get away with that. And now I really do feel like I could factor the V out. I'm going to factor it out on the right-hand side. And what I will be left with is A minus lambda I. And I'm writing that as I sub n just to emphasize the size of the matrix, but it's just A minus lambda I. So far, so good? So what I have here in this equation, guys, is I have a vector, it's V, it's not 0, that is being killed by the matrix A minus lambda I. When I multiply by A minus lambda I, it kills V. What does that tell you about V? Where does V live? If a vector gets killed by a matrix, do you remember from before spring break? It lives in where?
Null space.
The null space of that matrix. That's what I was looking for. Exactly. V is an element here. V is an element of the null space of A minus lambda I. That's exactly right. So what do we have? We have a vector V that's not 0, that's in this null space. So specifically what I could say here for sure is that the null space of the matrix, let's write it down again, the null space of A minus lambda I, that null space is definitely not just the 0 vector. You've got a vector V inside of that null space. Okay, this is all a little bit of theory, but it doesn't hurt to review a few things, right? We did a lot of this stuff back in chapter 4. So we have a null space that's not 0. What does that tell you about the matrix itself? Does that tell us anything about this matrix?
Its rank is not n.
Its rank is not n. That's true, and there are about 15 other things that you could have told me as well. Do you guys remember the invertible matrix theorem, the big long list, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? There's a whole bunch of things in here. One of the things it says about an invertible matrix is that its null space is 0. So if the null space here is not 0, then what are you going to tell me about the matrix? It's not invertible. That's right. It is not invertible. And what would be the best way or the easiest way or go-to way of deciding if a matrix is invertible or not? What would you, if I hand you a matrix and I say, is this invertible? What are you probably going to do? Take the determinant, right? You're going to take the determinant. And if the matrix is not invertible, the determinant of this matrix would need to be equal to 0, right? Because if the determinant is not 0, then the matrix is invertible. Okay. This is where I wanted to get to. I have exactly the right amount of space here. To find the eigenvalues, I need to solve for lambda down here. And once I have those lambdas, then I can find the eigenvectors by doing these null spaces. Do you guys like null spaces? Hope so. Unfortunately, we are going to be seeing a lot of them in this chapter. So what I'm going to do, guys, is an example. Okay, we have 5 minutes. I'm going to start today. We're just going to do an easy example. And then on Monday next week, we'll start into some slightly more interesting examples. The most important equation in chapter 7, right here. So the reason I keep saying that is because it tends to get lost. After a while, you start doing these determinants and doing these null spaces, and you lose track of where we started from. This was the starting point. Okay, let's do an example. I've only got 5 minutes. I want to get this, at least one of these in, so you guys have something to start thinking about this weekend on how this chapter is going to go. Here's an example. Oh, before I do that, sorry. I forgot one thing over here. I get so excited. This null space has a name. This is called the eigenspace. You have a little room to write that down. This is the eigenspace of A corresponding to lambda. And it's usually written E sub lambda. So I just wanted to write that down. The reason that, well, by the way, because it's a null space, it is a subspace. Null spaces, row spaces, column spaces, they're all subspaces. So it is a subspace, and if it's a subspace, guess what I'm going to ask you for?
Basis.
A basis, exactly. So let's do that. Let's find bases for the eigenspaces of, I need to write down my matrix here. We're just going to do a little 2x2, wrap up our class today. Quick little 2x2 example. All right, so how is this going to go? We're going to figure out the eigenvalues by using this determinant equation. So how does this work, by the way? We take the matrix A and we subtract. So this is lambda times the identity, right? So here I'm going to subtract. I'm going to turn these into lambdas, right? That's lambda I. Lambda times the identity has got a bunch of lambdas down the main diagonal. We're going to subtract that off of the matrix A. So we'll have 1 minus lambda, right? And then we'll have a -3. We don't change that number. The 1 doesn't change. And we have 5 minus lambda. And I am going to set this equal to 0. This is how we find the eigenvalues. And this is just a 2x2. Everybody good with a 2x2 determinant?
AD
Remember how that
minus
works?
BC.
AD minus BC, right? So we're going to take the upper left corner times the lower right corner, subtract the BC, which actually means we're going to add 3. So we set that equal to 0. Now I'm going to go ahead and multiply this out. If I multiply this out, guys, you're going to get lambda squared minus 6 lambda plus 8 equals 0. And this one factors very nicely, so let me just do it for you. It's just lambda minus 4 times lambda minus 2 equals 0. And so we get our lambdas. Lambda is either equal to 4 or it is equal to 2. Once you have it fully factored, which is what you want, you'll get your lambdas. Now, guys, here is the unpleasant truth about this. If you get the lambdas wrong, whole thing is screwed up. So, and how far away are we from getting the lambdas wrong? We multiply it out wrong. We accidentally, put the wrong number down, right? Very easy to sort of make a mistake with this. And if the lambdas are wrong, we're really sort of SOL. We can't do the problem because it's just not going to work. So I have a couple of fun facts I want to write down for you. These fun facts, and then we may have to just come back and wrap this up next time. These fun facts about the eigenvalues. These are fun facts about the eigenvalues that will help us to make sure that the lambdas are right. The first one is, if you add up the lambdas, I don't know how many lambdas you're going to have, but if you add these lambdas up, you have to get the trace of the matrix. Does anybody remember what the trace TR of A? You remember seeing that somewhere? This has been a little while, but I just want to remind you, the trace of a matrix is just the sum of the main diagonal. So however big that matrix is. So you just add A11 plus A22 plus A33 and so on. You just add up that main diagonal. So look at our example here. The trace of this matrix, 1 plus 5 is 6. So your lambdas had better add up to 6. If they don't, red flag, right? We got to stop and fix the calculation a little bit. Okay, and then the second fun fact is that if you multiply the lambdas, you're going to get the determinant of the matrix. I think we all know what the determinant is. So if I take the determinant of this matrix, right, 1 times 5 minus -3 times 1, that's 8. The product of the lambdas should be the determinant of the matrix. If either of these fun facts isn't being confirmed by your work, you probably need to get another check at the lambdas. Make sure that you get them right. Okay. I am out of time, unfortunately. I think what I'll do is I'll come back on Monday. We're going to do a much better example.
So are we fixing that example then?
I will probably try to come back to this example, or I'll have you guys watch it.
You didn't find the basic.
Yeah, I did not finish this example, guys. I'm out of time. I don't have time to finish it. So we'll do that next time. For now, I'm going to wish you all a wonderful rest of your Wednesday. Feel free to come by my office hours this evening if you have questions about the homework.
Get our exam.
Oh, the exams. Oh my God. Okay, hold on. Hold on. Nicholas. I've already sent you guys an email about this, so I don't need to give a lot of comments at the moment. But let me just try and pass these back to those of you who are here. Jesus. Matt. Gustavo. Go. Elias. Luis. What am I here? Dylan's not here. David is here. Lisa is not here. Kevin. Once you get your exam, guys, you're welcome to take off. Alexandra. Here, Anthony. There you are. Not here. Tina here. There she is. Nathan. Jade's not here. Lucia.
I did fine.
Parsa.
I really thought I bombed this,
Kelly. No, you did all right. Kelvin's not here. Raylene. Sebastian. Who else is waiting for a test here? Josh. And I will respond to your email. I'll send you an email. Oh, yeah. Take care. You too.
Yeah, when I saw this, I thought you put a typo, like it was supposed to be 79 or something.
No. You did fine. Bye, have a great day, Dylan. Josh. You're Josh, right?
Yes.
Oh, I'm so sorry.
It's okay, don't worry about it.
You too, bye-bye.